Next problem up is number 28. I haven't used asymptotes yet because they didn't come up, but I'm glancing at this problem. I'm trying to figure out the domain. I want x squared minus 1 to be positive. Look at the graph of this. It's much quicker. This is a parabola shifted down 1 unit. Where is this graph bigger than 0? So domain, negative infinity to negative 1, union with 1 to infinity. So on the graph, there is nothing between negative 1 and positive 1. There's nothing there. I am going to look for asymptotes in this case. This is not that traditional graph. So let's see. If I put x equals 0, we have a problem. I'll get 0 over square root of negative 1. You can't have a y-intercept. Right? Can I have an x-intercept? Can I set the top equals 0? Well, that only happens at the origin. There's no intercept either. An odd graph. If I take the limit as x approaches infinity, x over square root of x squared minus 1, limit as x approaches infinity, I'm going to divide the denominator limit as x approaches infinity, that's a 0. That is x over positive x. So that's a 1. That gives me a 1. That tells me on the long run the graph is going to level off next to 1. And if I take the limit as x approaches negative infinity, almost the same work. Do you know why this is negative? Because this is negative and the absolute value of x squared will give a negative x. So that's a negative 1. So I know the graph levels off next to the negative 1 on the left hand side. Alright, now what? Well, let's see. Nothing. So I'm going to write this as x into x squared minus 1 to the negative 1/2. When I take a derivative, that would be derivative of the first times the second plus the first. Derivative of the second is negative 1/2. Bring the power down, subtract 1 from the power, times 2x. So y prime is actually, if I factor, those twos cancel out. If I factor x squared minus 1 to the negative 3/2, I would have, when I divide those, x squared minus 1 minus x squared. Those cancel out. So y prime is negative 1 over the square root of x squared minus 1 cubed. I gotta start writing better. I don't like this. That's gonna be negative 1 over the cube root of x squared minus 1 square root. Same thing. Now, 1 and negative 1, there's y prime. There's nothing there because the domain doesn't allow that. Do you see that this is negative no matter what? So, it's negative on both ends. Well, that doesn't tell us much. That says f is decreasing from negative infinity to negative 1, union with 1 to infinity. No local maximum, no local minimum, not a big deal. Let's take the second derivative. I want to take a derivative of this. So I got y prime to be negative x squared minus 1 to the negative 3/2. So y double prime, bring the power down, subtract 1 from the power, times the derivative of the inside. The 2's cancel out. That is 3x over the square root of x squared minus 1 to the 5th power. So 1, -1, and that equals 0 and 0, but I can't have that. Y double prime. Well, in this case, if I pick -3, -3 times -3 is a negative. This is concaving down. If I pick 5, that's positive, concaving up. So we know that f is concaving down from -infinity to -1, and f is concaving up from 1 to infinity. And there are no inflection points. Now I'm trying to map everything on my graph to match. Well, let's see. F is concaving down, and let me just get the colors right. So concaving down -infinity. Well, since this is an asymptote and that's an asymptote, and since it's concaving up from 1 to infinity, and again asymptote and asymptote, and does it satisfy that it's always decreasing? It's always decreasing, it's always. And since you guys are fascinated by trig and you always ask for trig, might as well work ahead of you. Sketch a graph of this, and they restrict the domain for us. They say the domain is restricted between pi over 2 and -pi over 2. Very good. Well, let's see. Intercepts, if I put 0 in for x, I'll get 0. Very good. I got a point on the graph. Awesome. Now, if I take the first derivative test, right? Derivative of that will be 2 minus derivative of tangent is secant squared of x. That equals 0 when secant squared of x equal 2, and the secant of x equal plus or minus radical 2. The reference angle secant equal radical 2, which cosine is 1 over radical 2, that's pi over 4, and it should be in all quadrants, but I'm limited. They limited the domain, so it should be in quadrant 1, pi over 4, 3 pi over 4 is out of that region, and -pi over 4 to the left of that is out of the region. That's the only 2 points I gotta worry about. This is y prime and this is y. And if I pick a point to the left of negative, let's go with the right. To the right of pi over 4, let's say pi over 6. Now I could use pi over 2 for testing, but let's go by pi over 3. If I look at pi over 3 and I put it in there, and if you look at the triangle, there's pi over 3. This is 1, 2, radical 3. So this is going to be 2 minus the secant. The secant is the hypotenuse over the adjacent squared. That's going to be 2 minus 4, that's negative. If I put 0, cosine of 0 is 1. 2 minus 1 is 1, that's positive. And if I pick negative pi over 3, we know in this quadrant, it's still positive. Well, I'm squaring it anyway. That turns out to be negative. So out of this, this is what we got. We got that the function is decreasing from -pi over 2 to -pi over 4, union with pi over 4 to pi over 2. We know that the function is increasing from -pi over 4 to pi over 4. That means we have, out of those, we have a local max at pi over 4, plug that in. Tan of pi over 4 is 1, pi over 2 minus 1, and we have a local minimum at -pi over 4, that's -pi over 2 minus a -1 plus 1. Remember, this is 1.6 about, right? So, we have a maximum pi over 4 halfway through, and 1.6 minus 1, about 0.6, about right there. There's a maximum there. Maximums look like this. And we have a minimum at -pi over 4, -0.6. It looks something like this. Now we want to go for the second derivative test. And I really, let me get rid of that for now. If I take the second derivative, y double prime will be, bring the power down, subtract 1 from the power, times derivative of secant, which is secant of theta tan of theta. Y double prime is actually negative 2 sine of theta over cosine times cosine cubed of theta. Right? Now, let's figure out where that equals 0 and where is that undefined. Well, this would equal 0 when sine equals 0. Sine equals 0 at 0 or pi, but I can't reach to pi. And it does not exist when the cosine of theta equals 0. I should put that here. And that happens at pi over 2, but that's not allowed. So 0 is the only point I gotta worry about. This is y double prime, and this is y. And if I look at a point to the left, let's say negative pi over 4. If I throw negative pi over 4 in either here or here, this is negative 2. Negative pi over 4 is in this quadrant. In this quadrant, the denominator is positive and the top is negative. Negative times a negative over a positive is a positive. The graph is concaving up. And if I pick pi over 4, if I put pi over 4 and that's in quadrant 1, I have a negative 2 times a positive over a positive, that's a negative, concaving down. So I could here say, well, we have f is concaving up from negative pi over 2 to 0, concaving down from 0 to pi over 2. And we have an inflection point at 0, 0. So concaving up, let me get the colors out. If I want to go by concaving up from negative pi over 2 to 0, well, that's concaving up. And if I wanted to concave down from 0 to infinity, passing through that point, there it is. We couldn't find the intercepts because if I was to set this equal to 0, saying tan of x equal to x, that's not simple. We don't know where that point is, and we don't know where that point is. Algebraically, that is. Alright, let's see how much more time we have. I can't do another problem in that much time, so your homework is 1 through 31, every other odd, and number 37.